Hello students, welcome to Jceece Connected Selection number 24, Network Theory 18EC32. So this today's class will continue with a new topic, so that is node analysis. So usually so far we have discussed mesh analysis, source transformation, star delta conversions. So in those concepts we include KVL, Kirchhoff's voltage law, but in this node analysis, so we'll make use of what? KCL, it is Kirchhoff's current law. So we'll take one general example. So with one circuit diagram, so we'll write general equations with respect to a node analysis concept. So then we'll go through a particular example to solve some to find some voltage or currents through any branch or any node by using node analysis. So let us consider the circuit which consists of R1, R2, R3, R4, R5 and voltages VA and VB. So these are the voltage sources. Right, now in this mesh analysis we'll come across loops. Right, in mesh so we'll come across what? Loops. But in node analysis, so we'll come across what? Nodes. So this is the major difference. So in this case we need to identify the number of loops, but in node analysis we'll identify the number of nodes. How to identify the nodes? That is very important. The point wherein the circuit diagram which connects at least 3 elements. So here at this point, so which connects R1, R2, R3. So this we can call it as say node 1. Right. So at this same point, so this connects R2, R3, R5. So we call this one as say node 2. So even we can connect this one as a node also, but it makes a more number of equations to solve. It makes a tedious process, right? So for the betterment or optimize number of equations, so usually you will take the nodes wherein which connects at least 3 elements. So in this circuit diagram, so this is a node 1, this is a node 2, right? So one more node that is very important. So we'll connect this ground point as a reference node. So we'll show it as what? Ground, right? So if we have n number of equations, so or n nodes in the in any circuit diagram, so we'll have n minus 1 number of equations, right? So here we have the 3 nodes, node 1, node 2 and this is the node 3. This is called a reference node, right? So then more important thing is in the mesh analysis we will apply KVL, but in node analysis we will apply what? KCL. So most important thing is that outgoing currents are considered as positive. Outgoing currents are considered as positive. Incoming currents are considered as negative, right? One more thing, the nodes assumes that assuming that nodes are at higher potential. So this is very important. Nodes are at higher potential, right? Now we are trying to write the KCL equations at node 1. So we'll write this node 1 as say V1 voltage, node 2 as V2 voltage. As in mesh analysis you will write the like a mesh loop mesh current as X, Y and Z. Similarly in the node analysis we will write V1, V2, V3 up to Vn, right? Now what is the first step? Need to identify the number of nodes. We have identified the number of nodes are here V1 and V2, and then third node is what? Reference node, right? Now so I'll try to write the equation at node 1. So I'll write here, so KCL at node 1 or node V1. So I should write now KCL. So what is that? KCL states that incoming currents are is equal to outgoing currents at a particular node. Now I am writing with respect to this V1 node, right? So what we have assumed here, 3 points we have assumed here. So all outgoing currents are taken as positive, the incoming currents are taken as negative, and then node are at higher potential. So we are writing the equation at with respect to node 1. So means from this node 1 all the currents will go out, means comes out like this. We'll assume that this is the assumption. Similarly from node V2, this is the outgoing currents. From that node, particular node, the current will come out. Then they will reach to what voltage source to a current or reference node. Now, so I'll write KCL at node V1 or node 1. So with reference to this node V1, we are writing the KCL law, right? What is that current? From Ohm's law, we have V equal to I into R, right? So I want I, so which will be what? V by R, right? So I need to write V by R ratio, so in all the terms, right? So with respect to this point, so from this path I should write the current. So what is the current? Outgoing current. Since it is outgoing current, you should write it as what? Positive. So difference in the voltage at this path, so that is V1. We are assuming that it is higher potential, so therefore difference in the voltage is what? V1 minus VA divided by, in this path, what is the resistance appeared here? R1. That you should be divided by R1. Is it of this form? V by R. Why we have written V1 minus VA? So in this path, difference in the voltage is given as, assuming that we are V1 at a higher potential. So we have taken nodes are at higher potential. So you should write minus, because here it is a plus sign. So therefore V1 minus VA. So in this path, which is the resistance? R1. So this is the outgoing current, since it is, so therefore plus, right? Next, again here is the one more current which is outgoing. So V1 reference voltage is what? Ground, which is equal to what? 0. So V1 minus 0 divided by R4. V1 minus 0. Why? Because 0 is what? It's a ground, right? Divided by R4 plus one more is there here in this path, right? So what is the difference in the voltage here? V1 minus V2. Since we are writing with respect to V1 node, so V1 is at higher potential, therefore V1 minus V2. V1 minus V2. In that path, what is the resistance we have appeared? It is R2. See, with respect to this V1 node, all currents are outgoing, so no incoming currents, therefore is equal to 0. So you can rewrite this equation as V1 minus VA whole divided by R1 plus V1 by R4 plus V1 minus V2 by R2, which is equal to 0. Calls as equation number 1. Similarly, you should write KCL at node 2 or V2. Right? How to write that equation now here from this point? How many outgoing currents are, incoming currents are there? No, only all three are outgoing currents, right? Now we'll write this part of the circuit now. So KCL at node 2, that is V2. That is V2 minus VB. V2 minus VB. So in that, what is the resistance? That is R3 plus, again this is also outgoing current, V2 minus 0. Why? Because this is reference voltage, that is 0. V2 minus 0 by R5 plus, then this is one more path, V2 minus V1. V2 minus V1 whole divided by R2, which is equal to 0. No incoming current. So we can rewrite these equation as V2 minus VB whole divided by R3 plus V2 by R5 plus V2 minus V1 by R2, which is equal to 0. Calls as equation number 2. So compare the equation number 1 and 2. We have identified how many nodes here? V1, V2 and this V3, that is reference. How many equations we got? Equation number 1, equation number 2. Here VB and VA are the constants, like say 10 volts, say this is 20 volts. So only unknowns are V1 and V2. Then R1, R2, R3, R4, R5 are the resistors, constants values. If you know the R1, R2, R3, R4, R5 as well as VA, VB value, so we can easily identify the values of V1 and V2 at the same time. Why? Because we have the two equations, two unknowns. By taking a LCM, and we can solve easily the values for V1 and V2. This is what the introduction to the or basic concepts of node analysis, which is uses the KCL. This will be more clear if I take one example, so with the solutions that you will understand more. So now we'll stop it here. Rest all the things we'll discuss in the next class. Thank you.